here. All right, so thanks for coming, guys. This talk is titled Blockchain, from the Neurosis of Investor Mania to the Awe of Solid Tech. And it explores some of my journey, which began in the summer of this past year, summer 2019, when I started learning a little bit about this. Like I've been hearing about it for years, and I think like all of us, we distrust hype, right? Especially when you see every startup trying to list themselves as a blockchain company. So I was really skeptical about it being anything more than just vaporware, even though I'd heard about the success of Bitcoin. But I was just intrigued enough to start looking into the data structures first. And I was really blown away by the simplicity and the elegance of it. And then I started exploring more the process of mining, how to build a miner, how to solve blocks, how to assert validity. And then I started building on top of that the peer-to-peer networking. And I want to focus this presentation on the technical aspects of it. And I hope that by the end of it, that you guys will agree that there's some really cool stuff going on here, besides all of the investor mania. So the best way I figured I could do it was by building the thing. And just last night, I named this because I felt like I needed a name for this presentation. So it's essentially, it's a blockchain implementation. It's a cryptocurrency, and I called it Gilder, that G-U-I-L-D-E-R, because that's the Dutch word for their currency. And I grew up in the Netherlands, and I couldn't think of anything better. That sounds kind of cool. So I'll be calling my implementation of this thing Gilder. And for the most part, it's pretty similar to Bitcoin because there's a lot of resources online that explain the inner workings of it pretty well. And I use that as the foundation. And at the end of this presentation, we're going to be having a live demo of this Gilder implementation. And for anybody on the Validity Core network, if you're not on it just yet, if possible, if you get on it during the presentation, that would be amazing. And also, please do run this command that's at the bottom of this current slide and at the top of the video feed, because that will install the image that will allow you to act as a node in the network. So first of all, what is blockchain? Blockchain is just a spicy database. If I can get one thing across, it's this slide right here. So what is the secret spice? What makes it spicy? Some of the basics of this are that it's a ledger of transactions. You've probably heard that before, and it might mean nothing. But I hope by the end of it, you understand that it's essentially just the chain of blocks. It's a list of transactions that use the blockchain technology as a way of allowing you to have a decentralized network where all peers are created equal, and some guarantees of immutability. So another way of thinking about this is it's a commit once, read only database. There is no update command in a blockchain. We're going to talk a little bit about that, but I'm specifically going to be focusing on the beautiful and simple data structures, some of the elegant math that makes this whole thing work, peer-to-peer networking, and I hope that you guys agree that some of this stuff is kind of kick-ass. So what isn't it? It's not magic. It's not the answer to every modern problem. Blockchain is not equal to Gilder. Blockchain is not equal to Bitcoin. Blockchain is not equal to cryptocurrency. Cryptocurrency is not equal to Gilder. So we use those terms interchangeably, but they're very distinct things. And there's a hierarchy. And at the bottom of the slide, I'm showing that blockchain is essentially the backbone of all blockchain implementations. There are applications of blockchain that use it as a backbone, including cryptocurrency. And then you have implementations or instances of those applications. So Gilder, the cryptocurrency that I wrote, is a cryptocurrency which uses blockchain as its backbone. It is its data structure. But blockchain, the simplest state is just a spicy database. that allows you to do cool things with it. It's just the data structure, really. So let's talk about that data structure. Every single block is composed of by two things. So I think it's appropriate that we draw one of these blocks as a rectangle, right? And the two things are headers, which is this top section. Oh, this is dying. And transactions. And the headers have a few things in them. They've got 1, 2, 3, 4, 5 things in them. 1, 2, 3, 4, 5. And the only one that we're going to care about for this particular part of the talk is the previous hash. The previous hash is a pointer. The pointer to the previous block. So you hash the previous block, you get an answer, and you include that in the next block so that they're pointing to each other. And I'll show why that's important just a little bit. First,
real quick pause. So because we're recording this, I don't think we've toggled to the whiteboard with what you're drawing right now. Do you want to try disabling your sharing? And I want to see if then it'll switch over to the camera.
yeah.
I think
You read my mind.
All right, great.
Okay.
Can you guys all see the camera feed now?
And would you switch that to presenter instead of gallery in the view?
Might be better to use a dark marker too.
Yeah, I'm gonna give up on green real quick.
All right.
I can try to-
Speaker, thumbnail.
Yeah, if you click on speaker view, this is to all of the attendees, not you presenting. But yeah, if you just click on speaker view up in the top right hand corner, it'll make the window big, and yeah, we can see the whiteboard great.
Okay, yeah. All right.
Apparently that works for them.
Cool.
Thanks for
Sorry.
stopping that situation. So here's our first block, and we can call this the Genesis block. So the previous hash does not exist. This thing is essentially empty. This is the creation of the blockchain. Every single chain starts with one and only one Genesis block, and everything else gets mined onto it. So the next thing that, or the next block is, let me give this green marker one more shot here. But it looks exactly the same. It has all of its headers and its transaction. There's only 4 headers here apparently. And this previous hash is the hash value of this entire block. So all of the information gets rolled up. It gets included in the hash and is being pointed to by this guy. So block, block, blockchain. All the blockchain is an array of blocks. So this is kind of a cool way of thinking about it, but I think a more effective way to highlight the immutability of it is by thinking of them as being nested within each other. So now we're going to go to black. So unfortunately, this first one's going to be a little small, so I hope you can see it on the camera. It's small purposefully. So it's got its headers and its transactions. And when it's being pointed to by the previous one, you can kind of think of that as the next block composing it. So we've got all of our headers up here, and one of them is a previous hash, which is this whole previous block rolled up. So then the next block is an even bigger one. And it's got its headers and its previous hash is pointing to this block, which is pointing to this one. So you get this sort of nested, recursive relationship. Why is that important? Because this is what guarantees the immutability of the thing. Because we're mostly, if not all, software engineers here, we understand how hashing works. If you change even a single bit of the input value to the hashing function, you get a wildly different answer. So if somebody were to tamper with this inner block and say that instead of Bob giving Sally 100 guilders, he gave her 200, this entire thing breaks. Because every single peer gets the chain, they cycle through every single block, and they know that at some point something's been broken. So that's the data structure. And that's the cornerstone of the technology. So now let's cover what mining is. Just like blockchain was a spicy game of, or a spicy database. Why is my screen looking so weird? It doesn't look like that on my screen.
Go back and forth.
There we go. All right, so mining is a game of limbo. It gets harder the lower the bar is, right? And the bar is lowered by more miners or more peers being part of the network. And with a lower bar, it's that much harder to tamper with any information that has previously been added, because you need to find a new hash that works with your changed data. So it becomes more immutable the more miners are added to the network. So the game of limbo is a race. Everybody's racing to be the first person underneath that limbo bar. And it takes a lot of work in the process. And the winner also gets a reward. In my implementation, the winner gets 100 guilders. It's all arbitrary, but if enough people believe that means something, it does. And that's kind of where the concept of money comes from. With trust and belief comes value. And it uses hashing for every single attempt at getting underneath the target or the limbo bar. And a hash, specifically SHA-256, which is what I used for Gilder and what Bitcoin uses for its protocol as well, essentially gives you a random number between 0 and 2 raised to 256 minus 1. I'll cover what that nonce is in just a little bit. First, I'm going to stop sharing and get back over here to the board. So here's our game of limbo right here. We have a hash value on the y-axis. We have an attempt of mining, essentially a number of the nth number of hashing on the x-axis. So the hash value is essentially a random number between 0 and 2 raised to 256 minus 1, which is an enormous number. I have a slide talking just about how huge that number is. So the game is to find a block that hashes to a value that's underneath the target. So I'm going to draw this target out here. And that's just the number that you get from the hash of the thing. And the more difficult it is to solve, the more miners that are currently on your network, the lower the target goes, the lower the limbo bar moves inside of this, this environment. So if we hash 5 times, if we hash the block 5 times, I'm going to hypothetically say what we might get. We might get a relatively high number, something up here. Second time, and I started at 0 to the program, second time we might get something just above the target. Third time, we might get something somewhere in between. Fourth time, we might be a little bit higher again. And fifth time, let's say, it came out right there. We've just solved a block. So this makes you very happy. New block. I'm going to pause there for just a second because some of you guys might be asking, wait, how do you get different values for hashing a block? The answer is by changing a little bit of information inside of it. And that thing that you change is called a nonce, or an n once, some people call it. And it's just a number in my implementation that on every single attempt, I increment it by 1. So I get a wildly different hash value. That is one of the headers. Nonce and nonce. So when you hash this thing, or when you hash this thing with a nonce equal to 0, you get a wildly different answer than when you hash it with 1. At this point, I'm not going to talk too much about peer-to-peer networking just yet, but at this point, it's the responsibility of the miner to yell as loudly as possible, talk to all of the peers that it knows about, and shake them by the collar and say, I found the answer. And if the peers accept it, it gets added to their blockchain as well. And if 51% of the nodes all agree that that passes, then you've just earned 100 guilders. And it comes out of nowhere. It's the only way that new guilders get added to the chain. Every other transaction is just moving it from one place to another. The process of mining is where money comes from. And it's also what gives the blockchain certainty of immutability. Because it takes so much work to do this. It would take so much work for a cheater to find the answer, overwriting history in such a way that they create something that they want, giving themselves more money or something like that.
Hey, Andrew, I got a question for you.
Yeah.
This is Josh Badger, by the way. If you, and feel free to skip this if you're covering this in an additional slide, but like functionally, what is the role of a new block discovered?
The function of a new block is to commit a transaction into the chain.
Okay.
Because while you're mining, the new block transactions are coming in, and we're gonna experiment with adding transactions to the network. And you have an incentive as the miner to add those transactions into the block through your transaction fees. So you get a little bit extra than just 100. I haven't implemented that yet because it didn't seem all that interesting. It's just kind of an addendum to the process. But once you add that block in, it has all of the transactions in its payload. And at that point, you've committed money into the chain. And one of those transactions is your reward. So when you start a new block candidate, the first thing you do is you add your own little transaction in there that says, hey, I want 100 guilders for this. It comes from nobody, and every node agrees that's okay. And then other transactions come in through during that process and get added to the block. So mining adds new blocks, which is incentivized to the miner through the creation of new money. And as an incentive, through it as a process, it commits new transactions into the chain. Did that answer it?
Yeah, I think so. So I think the big takeaway is that a block enables more transactions to be recorded. It's like at the point in time where when someone solves the block, like any transactions up to that point get shoved into its transaction block within the block, and then that all gets committed.
Yeah, essentially. Anything since the last block.
Okay,
Create a
cool.
pool of
Okay.
transactions, and you try to load them in.
Yep. Okay, thanks for that.
Cool. So now let's talk about what happens after this. You just mined your first block. You got 100 guilders, which is really cool. But you get right back to work the next Monday. And you keep hashing. So your next hash, you might get this number. You might get this one next. You might get really close here, and then somebody else beats you to it. At that point, you get a request saying, hey, I think I found the answer. Somebody grabs you by the collar of your shirt and yells that they found the answer. So regrettably, you decide to check your math. It's on you to only accept blocks that make sense. Because otherwise, when you start mining on top of it and you find something, you put in a lot of work, you tell other people, they check somebody else's math and they see that it was founded on something that was wrong. So they're going to throw your chain right out the door. And all of your work was done for nothing. So when does this bar move? I think I have a slide for that. I might need to move a little bit faster to get to the demo. Oh, all right. Let's pause here for just a second to give you all a little bit of intuition about just how gigantic this number is up here. So all of these 1, 2, 3, 4, 5, 6 ways of showing that same number are identical, except for the last one, which is rounded. But 2 raised to 256 minus 1 is equal to that giant white slice. It's equal to all of those F's in hex, all of those 1s in binary, and in decimal, that gigantic number. And if somebody knows how to pronounce that number, I'll give you the biggest high five you've ever seen. And then scientific notation is that last value right there. And you can see that that's over 3/4 of a Google, which is just an astronomically high number. And dealing with this presented a little complication for me because there are no primitive data types that allow you to work with this size number. So how is difficulty adjusted? So remember that difficulty is the inverse of the target value. So as difficulty goes up, the target or the limbo bar goes down. And we need a way of responding to more miners coming into the pool. Why? Because my protocol is looking for a new block being solved on average every 10 seconds. So when we're all mining later, somebody should jump up in excitement on average about once every 10 minutes. Or sorry, 10 seconds. And it could be as quickly as the next hash. It could be a millisecond, or it could be 10 minutes. Nobody knows. It's the process. There is no getting, there is no percentage towards the next block being solved. There's only a statistical likelihood of it happening next. And so the more mining attempts you have, the higher the likelihood of solving the next block. And to maintain an even distribution amount of time between each one of these block solves, we adjust the difficulty. And the way that works is actually really elegant and straightforward. When I got this, it was kind of an aha moment that made me see that difficult things are just the composition of a bunch of rules of simplicity, right? But my protocol, which is really similar to Bitcoin, is it looks back at the last 10 blocks. When it reaches a chain length that's divisible by 10, mod 10, it looks at the last 10, it calculates the total amount of time, divides that by 10 to get the average duration between each block, and then adjusts the difficulty by the discrepancy. So if you're shooting for 10 seconds between each block, the last 10 took 5 seconds, all you do is you double the difficulty. You lower this thing by a factor of 2. And then for the next 10 blocks, you should be that much closer to evening out on the right amount. And we'll see when I first start mining that the difficulty is going to be way off. So I'm going to shoot through a bunch of blocks all of a sudden, and over time, the right difficulty is found. We reach some stabilization until more miners come in, at which point we need to respond to that. And that's done through this process of looking back in history and comparing against how long you want things to take. All right. So, peer-to-peer networking. This is kind of the cornerstone of the way in which rules are enforced. So, I'll bring your attention over to the board once more. And we'll talk about a hypothetical network of 4 nodes. So when we start this thing up later, I'll be the first node in there. Me. And I've got a little miner going on in the background. But more than that, I'm going to be advertising my IP address and the port to reach my node. So the next person to join is going to first go through the process of peer discovery. I'm going to tell you guys all my IP address so you can reach out to that if you're on the network. And then you'll need to, your node is going to reach out to mine, knock on my door, and it's also going to pass along the return address. Because unfortunately, when you work with Docker, the IP addresses using gRPC get dropped in the process, so you need to manually say where you're coming from. And it's very important you get this right, because if you don't say where you came from, I'm not going to be able to tell you when a new block got solved, and you're going to be living in history. And your chain is going to be much shorter than the others. And peers only accept the longer of two chains. So if everything goes well, then I'm going to respond back to you with, and who wants to be this one? Nick, is this you?
I'll be that.
You second one in?
Yeah,
Okay.
let's do it.
So Nick comes in, and he's also mining. And I tell him all the other peers I know about, which at this point is none. And we got a third coming in. This is going to be UKC. And you're first going to reach out to me because you don't know about Nick just yet. I'm going to respond with all the IP addresses I know about. So you're going to know about Nick. You're going to reach out to him. And he's going to reach out to you. We have this kind of backwards thing going on here. And then Rebecca comes in. And she does the same process, reaches out to me. I tell her all the IP addresses I know about. She reaches out to Nick. He tells her all the IP addresses he knows about. And then Casey. So all of these people are talking to each other. And you might be wondering, in a lawless land such as this, how is there consistency? How are there rules? How do you determine what is right and what isn't? It's a real social network. I kind of think of a peer-to-peer network as being a group of people. There are rules, there are cheaters, there's verification, and there are people that need to check to make sure that everybody's playing by the rules. Because if you're not playing by the rules, and other people realize that, you're not going to be solving any new thing. You're not going to be making any money. And in the same way, if a cheater gets past your guard, then you've made a mistake. And if somebody checks their math through you and realizes that it's invalid, then again, you're out of the game. So every single node, every single peer in the network is essentially a vote. It's a democratic society. 51% of the votes determine how this thing acts. In a way, it's an ecosystem. It's kind of beautiful. My peer-to-peer network is pretty simple, but works pretty well. So there are incentives to play by the rules. Okay. You guys can see my screen again? Okay. So transactions, we haven't talked much about transactions just yet, but this is kind of the cornerstone of this entire situation. So along with that image that I asked you guys to pull down, lives a client where you can interact through the command line like a Coinbase. And you point to any one of these nodes. It could be me, it could be Nick, it could be Casey, or Rebecca, and you submit a transaction. So the transaction is first verified and authorized. You provide your private key, which I'll talk through in a little bit. And then granted that it's accepted, that node is responsible for propagating it across the entire network. Because when it solves a block, it wants other people to say, yes, that transaction that's in there was actually submitted and it is legitimate. Again, everybody needs to play by the rules because cheaters are ousted. And then the transactions get bounced throughout the network and they get committed into the next block. And that's some of what Josh was asking about. So good, we're doing well on time. My implementation uses Golang. I use gRPC for all of the networking between all of the nodes, and everything is Dockerized. So when you guys pull this image down, your node is going to be living inside of a container and interacting with the rest of the world. So just as a disclaimer, the public and private security is not fleshed out. So this is not a fully fleshed out cryptocurrency. It's a proof of concept. And I do want to get into the public-private key cryptography side of things, but just didn't have enough time to do it beforehand. It's kind of a pseudo situation where you have a private key that you'll choose, and we hash it using the SHA-256, and then that will create your public key. So let's switch gears for just a couple minutes and look at a little bit of code, because I want to show you guys how simple some of this is. Does anybody know how to zoom in IntelliJ editor?
Command plus.
Command Shift plus?
Command block should do it.
It's not working.
Get a weird key mapping.
I think you have to go to
Oh,
presentation mode.
Go to what?
Presentation mode.
That'll definitely zoom in. Then you can't switch files or do anything else.
is that legible? It kind of looks okay to me.
It's fine for me.
All right.
Yeah, it's legible to me.
All right, great. So this is my protobuf implementation. All the data structures and the RPCs that control the entire network. And I just want to show you how dead simple the blockchain data structure is. Look at this. This is the block. This is the entire thing. It has a timestamp, the previous hash, which we've covered, the nonce, which I've covered, the target, which I've talked a little about, and a Merkle root. And what the Merkle root is it's essentially just a rolled up hash of all of the transactions. So it's a way of asserting that all the transactions are in this thing really quickly and easily. But that's the block. Oh, and the transactions, a list of transactions. And a blockchain is just a repeated chain of blocks. Like I think it's so simple and so elegant how easy this thing is. The data structure is just so straightforward, yet it allows for all of this cool stuff when you build upon this backbone. I'm going to scroll down here. I'm going to actually skip over the all right. The transaction is just who's giving money, how much, and to whom, and a message and a hash. But I'm not going to talk much about that right now. And this service node right here is all 5 RPCs that are exposed by each one of these nodes. So Discover is used for peer discovery. You knock on somebody's door and they tell you all the friends that they know about. It's very transparent. Mark Zuckerberg would be very proud. Get state is something that's used when you first join the network. You find out what the longest chain is, what's the current difficulty, so that you're caught up to snuff. Share chain, this is you yelling to solve the next block. Share transaction, that's the propagation of transactions. And get credit is a little something that you can use through the client that I built onto this thing. So you can see how many guilders you have before trying to submit a transaction. Okay, and let's look at the miner. So the miner is running in a Go routine. 1 to n number of Go routines. You can run as many concurrently as you want, but we're just going to default to 1 here. And it's just a loop over and over and over until the context is canceled. That takes a candidate block, which is the rightmost block in the chain that I drew up on the board. And then it just creates a new block from the previous hash, all the transactions, the nonce, the target, and the public key of the person who's mining this thing. It hashes it, and then because these numbers are so gigantic, I needed to use the Golang big library, which actually worked really nicely. And I'm just comparing the hash against the target. Did this block make it underneath the limbo bar or not? If it did, so this convoluted bit of garbage right here means that it was less than or equal to the target. but it's important that this is very, very terse because this loop needs to be extremely efficient. If it got under the bar, then it's considered solved. And what it does is it just bubbles up the report of the new block to the parent that called this thing. And then it updates the previous hash to the hash of the new candidate block, where the candidate block, which is now the new committed block, and it keeps hashing on that one. So the miner gets right back to work right afterwards. And if it doesn't solve the thing, all it does is it increments the nonce and it tries again. It goes back at the top of the loop. It alters the hash or the block, gets a wildly new hash, and it checks, did I make it underneath or not? So this is the work. This is the insane amount of power consumption that the Bitcoin protocol undertakes. And when we all start mining later, we might hear all of our fans roaring up. And it'll be because of this loop right here. All right, so that's it for that. I don't have time to go over these other two snippets of code. So let's start mining, because I know this is the moment you guys have all been waiting for. So for the remote people, unless if you have the Broomfield VPC, unfortunately, you're not going to be able to mine with us. But if you look at the instructions on this GitHub page, you might be able to find a way of creating your own little network if some of you are in the same network. So feel free to talk amongst yourselves there. But for all the people here in Broomfield, if you haven't already installed or downloaded that image, please do so now. And then direct yourself over to that GitHub page where we're going to copy some commands. So under that run node section, you'll see the Docker run commands. Let's pause there for just a second because I'm actually going to get my miner up and going so that I can be the seed for everybody else. Sounds weird when you say that. So if you have a look at this command right here, I'm just running the image. This is an optional step for you guys, this volume mounting of the storage. Do include this if you want to look at the ledger afterwards, if you want to view it in JSON or whatnot. But if you don't want to create that thing locally, then I won't force you. This blockchain key is your private key. So I'm exposing my private key to you guys right now, which means that later you're going to be able to personify me if you want to send transactions around. But I'm not too worried about it because we're probably just going to discard this ledger after.
Can it be numbers?
Yes, you could put numbers in there. It's just it'll treat it like a string. This seeds command, I'm leaving empty because there are no seeds before I create this thing. But the return address is very important because that's what I'll tell you about when you reach out to me. You will need to put my IP address and port in for that seeds command. So I'm going to get myself started. There we go. And you can see every single line here is a new block that I just solved. It skipped through a bunch of them because the difficulty was way off. And you can see every 10 blocks, I'm readjusting that target. The hash of the target over on the left and the hash of the coin or the block that solved it underneath there. So now, why don't you guys go ahead and start running that commands, and to find your IP address, the easiest way that Zach told me about yesterday is if you're on a Mac, hold down the Option key and click up on your the Wi-Fi symbol. I can't see it because Zoom is away. Hold Option and click on this this Wi-Fi button. And then directly underneath Validity Corp, you should see your local IP address.
Did you share your IP address?
It's on the board.
Okay,
I
cool.
thought that was just an example.
Yeah.
Ooh.
And I did also have it in the slides.
Oh, I can't read.
So pick your own blockchain key. It can be whatever you want. Just make sure that it's new. Oh, I see the first peer. When you first start running this thing, you'll see what your public key hashed to. So who's 2FDF?
Me.
That's you?
Yeah.
Nice. I should have put you down as the first one.
Yeah.
There's another one. We
That's
got 773. There's 834.
So for, out of curiosity, so for anyone remote that's not in the office, that initial command that Andrew showed, it looks like you could set up your own, someone could set up their own seed using a similar command, providing their own return, their own local IP address as the
The return
return.
address.
Yep.
And empty for seeds.
Yeah.
And then have other people connect with you.
I was also thinking, like, I don't know exactly what the IP space looks like for when people connect to the VPN, but that might put everyone on the same network if a bunch of people just connected to the VPN real quick and tried it.
Yeah.
Um,
I'm hoping that the VPN is going to work.
I'm trying to set one up right now.
So I can tell just by looking at these. Oh no. Just got a seg fault.
Test spoken.
There's got to be at least one in every demo.
Yeah, I only stress tested this against 3 computers before, and it's been totally fine. So the good thing about this is other people should still be mining. So why doesn't somebody tell me your address, and I can just join you guys again?
I'm at 10,
10,
0, 247.
247.
Yeah, it's up there.
Find me and all my
That's
friends.
also in
See if I joined.
here.
Who are you?
Zach.
What's your?
Mine's 192, 168 because I'm on the VPN.
See it.
Maddie, what IP address were you saying?
I said I have 192, 168, 100.104 because I'm on the VPN.
I don't see it.
Yeah.
I think the VPN is going to be a
It's like-
1010 network.
It looks like it's doing stuff, so I don't know.
But
Did you connect to any peers? Yeah, it looks like.
It looks like it's doing stuff. Maybe that address is wrong. I don't know. That's what I put in there. It seems
right.
to be going.
I wonder if your return address is right though, because I don't know if I've gotten you. I think I'm only
Oh,
connected with
half
5 other
connected.
peers right now.
Between Docker and the various subnets, it all gets a little tricky, but
yeah.
Yeah.
Should I just
you get the
say
idea.
Like,
You just mine one right there.
Hell yeah. Andrew, how does
Connected though, 'cause you're not getting other people's.
the first block get created? Because there's no previous hash.
Exactly. Yeah. So if you reach out to people and you don't see any, if you are the seed, then you just create an empty block, and that's it. You get to claim that as your own transaction, so you make 100 guilders off of it. But it's just the anchor, and it's not really a very useful thing because the only transaction in there is your reward.
What if multiple people join simultaneously and simultaneously create an empty block?
Then whoever adds the second one first is going to win.
Okay.
The longest chain wins.
Okay.
All right, so I'm seeing more peers joining, which is awesome.
I mean, I don't know.
Oh, okay. So I haven't really want to get in.
It only has me.
Just adding.
So. Did you get on the
Okay.
VPN?
What would you have for seeds?
The Cisco VPN or the?
No, the Aruba VPN because the Aruba one is okay. It looks like it's adding peers now.
Yeah.
Okay. Still have the Aruba one.
Oh, 24.
Yep.
How do you fix the Docker run?
We're gonna go a hot minute there. Like the RP-corp.
Yeah.
That's the one I'm using. Yeah, I haven't used that Cisco one.
You want to see if there's any questions? Is this kind of, or you want to?
Have people add some transactions. All right. So for those of you still trying to figure it out, please do find a neighbor who gets it or who's gotten in. And for everybody else, you hear some of those fans running, by the way? It's getting toasty in here. We are burning through electricity. My battery is dropping stiffly. But
It's just for a minute.
for those of you who would like to try adding some transactions to this thing, take a look at that GitHub page again, and scroll on down to the node client section, and copy that Docker run, the first one for the submit transaction. You could check your credit first if you wanted to, but if you try giving more than you own, it'll tell you how much you have. So go ahead and run that. And you can point it to any node that you want. Since you already know what my IP address is, you can just point it towards mine and I'll propagate it for you. But you could also point it to your own IP, and then your node will propagate it for you. So I'm gonna run my transaction.
And that's 0.2. You getting there? Yeah, I'm marked.
Recipient pub key.
Yeah, so recipient pub key could be anything you want. If you want it to go to somebody that's mining, you can just copy it from one that you see in your console. Otherwise, you can just create something and it'll reward it for that person.
What's the sender key?
Sender key is the private key that you use to create your node.
Okay.
In my case, it's AS gains. All right, so I'm gonna try submitting this.
There I go. Into the transaction.
No, the pub key owns 0. Insufficient credits.
Insufficient credit.
What? We're broke.
How much do you have?
It says
I
0.
own 0.
Yeah. Well, the key I put in mine? My
Uh,
pub key?
Your private key.
Yeah. Oh, maybe I put it in wrong. Let me go double check what I put in
So
there.
recipient is one of those big hashes that I see?
All right, so I'm seeing some transaction popping up here.
Yeah, I think so.
Awesome.
It's one of these things for the recipient?
The
I'm
recipient can be
probably
anything
not
you want.
connected. Like, I don't
It's not the same area either.
Okay.
Recipient can be anything I want.
Yeah, you can choose a pub key that exists.
Yeah, I
but
tried
if
that.
you,
But it said 0, I think.
yeah, so it's saying 0 about your sender key.
Oh, my
It looks
own.
like that's
Okay.
something.
Well,
That's fun.
that was what I thought I put it in here. Let me see. Mali cool key. This key, blockchain key.
Yeah.
And then for my other key, I
Oh,
just stole this.
I
or,
don't
like,
think you're
what do we
actually
want?
connected to the network.
Yeah, because I'm only seeing me
Yeah.
popping up over
Yeah.
here. Yeah, makes sense.
Unfortunately, you're not
Dang it.
your return address.
I'm all alone.
Oh, yeah.
I'm only
So sad.
here.
Sender key is.
Sender key is your private key you use to
Okay.
create your
Someone connect
node.
to mine.
But isn't that your?
Oh, I see. So if I wanted to write a transaction that gave me money,
Oh, I
then
can
my
use
recipient should be my
yours.
hash. So I did the
You
sender.
could, yeah, but then you're just giving money back to yourself.
My IP.
Yeah, that sounds right.
Like nothing's destroyed there.
Yeah.
As long as my
I thought I
code
would
was right. Look at that. The second to last block took 55 seconds to solve. Some of these are only taking a second, 1.6.
That's just
Is
Somebody's
11.
computer is like way better.
Yeah.
What's going on?
And if you look at all of these difficult, scroll through all of this.
I mean, I did have. Now I have 0.
Okay, so let
So
me send you.
check this out. You see
I just
this?
sent it out.
This is one of the first targets. See how it only has 3 leading zeros? That's a relatively high number. But over time, as more peers come on,
I thought I would.
So
it's more difficult.
That's his.
So there are 4 leading zeros. And right now, we're up to 6.
Yeah, I went through other one.
More compute power is being added onto this thing.
So you're talking about the.
Can you
Like,
talk
this-
about what's in the
this thing
blockchain
right
storage?
here. What is this
Like
here?
there's the
Yeah.
blocks and the
Yep.
periods.
Yeah, I'll
So
just
that's
need to
me.
send a second.
I'm gonna send you a
Okay.
fast.
Periods? What?
Adjust
Is, it, is
All
yours
right.
printing out more stuff? That
I'm gonna back out of the network. If you guys want to keep mining, go right on ahead, but I want to start showing you guys the ledger. So my node is shutting down and I'm writing my chain to the blockchain storage location. If you did volume mount that in, you can check that out later afterwards and you should see all of our transactions and have a jolly good time. But I'm printing out the JSON version of the blockchain. And each one of these right here represents a full block. This one only has a single transaction, which is the block reward transaction. And it was given to whoever F4A was. Congratulations. Look at this nonce right here. Look at how massive that number is. That means that this node tried 3,849,937 attempts before it finally found a hash that made it underneath that target. That's an insane amount of computation power. And this one right up here, look, it's only 711,000. What is that, like a quarter or no, about a fifth of the amount. So it's all random. This could be as low as 0. Every time a new block is solved, the protocol resets the nonce down to 0, just so I can see how many it was. It could stick at exactly where it was before, and it'll be just as random with a new block. But every new block starts at 0, and it could solve it on that first try, or it could take a lot longer. Let's take a look at this block, though. This one's a lot more interesting because it's got 5 transactions. The first one is the block solve reward. It was solved by F4A. Oh, same miner. You got both of those. Nice. So they get 100. And then there were a few transactions, 4 of them. Looks like somebody tried sending it to me, which is really sweet. That was my private key, but unfortunately that's not my public key, so I didn't get anything from it. And they left the message as optional, which is cute. Here's another optional. They sent 10 guilders. This one sent 20 with a message of payment. And this person tried sending, it was the same sender. Oh, they tried sending things twice. That's sweet. Yeah, so there are quite a few blocks on here. And I want to try to show you guys one more thing before we go to questions. I wrote a little program that analyzes the durations between all the blocks. If this works, it might be really cool. Yeah, look at that. So these are the average amount of time that it took for every single, every block, looking back 10 blocks. So it's a rolling average. When we first started, I was very, very low because the difficulty was too low for the amount of hashing power. But over time, look, we settled out around 10 seconds, which is what we were shooting for. And as we got a bunch more miners on, it looks like we skyrocketed up here. And I would venture that if we kept mining long enough, this would gradually come back down to 10 and stabilize around 10, assuming that it maintains the same amount of hashing. So yeah, am I sharing now? Good. That's it. Do you guys have any questions?
So is like how you determine the difficulty the biggest differences between different cryptocurrencies?
That's a big difference. There's also huge differences in the way that work is added. This is a proof of work cryptocurrency where everybody's mining and it just takes a lot of compute power. There are proof of stake cryptocurrencies, which I know very little about, but it's an alternative way of doing things. There are some cryptocurrencies that optimize for stability. So specifically stability of the currency, because they think one of the problems of Bitcoin is the giant fluctuations in the value of the actual coin. Bitcoin aims for 10 minutes between each block on average, minus 10 seconds. And they also look back 2016 blocks. I'm going to look back 10 because I don't think we even got to 2016. And I wanted to see a bunch of target changes. So that's one of the big differences. And then probably lots in the protocol for the way the peer networking works as well.
I thought like the problem with cryptocurrency was that it takes so long for your transactions to go through, but you said it only takes 10 minutes to solve between blocks. So does that mean my transactions only take like 10 minutes to go through, or is there too much time spent like verifying afterwards?
Yeah,
Why
so
does it take so long?
it can take a long time to get the information actually propagated across the network because Bitcoin is so huge. Your transaction can be in what they call the mempool, a transaction pool, for a long time before it's actually committed in, because they can queue up there for a long period of time. I don't know why that is exactly, and some cryptocurrencies they optimize for more transaction throughput, because that is one of the big problems of Bitcoin, is that the throughput is relatively low. So, and there's another problem that I think you're highlighting, which is the possibility of having history being overwritten. The more blocks you have, the harder it is for a cheater to overwrite history, right? Because they have to duplicate all of that work that went into solving that thing. So often people will wait for their transaction to be 2, 3, 4 blocks in before they have enough confidence that some competing chain isn't going, like on the opposite side of the world, that's still trying to find its way over, isn't going to replace yours. That's one of the reasons that people wait a long time. Any other questions? I know we've covered a lot.
So are you a miner?
Andrew, this was
Never
awesome.
mind. Thanks.
I'm glad we recorded this. That way I can play it 3 or 4 more times.
Oh, there's so much more I want to talk about. Like I could easily talk for another hour about the vulnerabilities in this thing and the
Part 2.
difficulty of propagation and
And
balancing
maybe
networks.
we can do a blockchain club and meet around beers and all get the different seeds running.
Make a
Sounds good to
validity
me.
coin.
Yeah.
Any other questions? All right, well, we ended right on time.
Really cool. Thanks.
Thank you.
My favorite one was Dogecoin.
Yeah, that was started as a
They
joke.
wanted to go to the moon. They did. They went to the moon.
Well, the memes from that,
Yeah.
like, alone, like,
I'm pretty sure they got a sticker on something